Prove that d by dx of a constant times f of x equals the constant times d by dx of f of x. So where c is the constant and f is a differentiable function. In other words, when you take a derivative, you can pull the constant outside of the derivative. So before we go ahead and prove this, let's take a look at an example. Here I have two different functions plotted. I have this one here, which is just the square root of x. And here I have 2 times the square root of x. So in this case, our constant here would be 2 that we're multiplying by. And the effect of that 2 is to stretch out the graph. So it's been vertically stretched by a factor of 2. And let's look at the slopes of the tangent lines at x equals 1 for each of the graphs. So that's going to look like this. The red line is the tangent line at x equals 1 to the graph of the square root of x, and the blue line is the tangent line at x equals 1 to the graph of 2 times the square root of x. And what do we notice about the slopes? Well, it turns out that the slope of this red line right here, so the slope of this, ends up being, if you were to take the derivative and calculate it at that place there, you would see that the derivative is a half, or the slope is a half at that point. This is at 1 right here. Well, it's a line, so that's the slope is the same everywhere, but I'm looking at the line at 1. What about the blue line? That looks like it has a larger slope. How much larger? Well, the slope in this case, if we were going to follow the rule here that we're trying to prove, the constant can be pulled outside of the derivative. Remember, the derivative is the slope of the tangent line, so really it should be 2 times this, and in fact it is. It's 2 times a half, which is 1. So it kind of makes sense with this specific example if we look at it graphically, but this is not a proof. Let's try and do a proof. Okay, so to do a proof here, I should probably start off by defining some other function here. So we'll say we're going to let g of x be a constant times f of x. So now I can rewrite my limit definition of a derivative in terms of g of x. So the limit as h approaches 0 of g of x plus h minus g of x all over h. Okay. All right, so now g of x is my constant times f of x, and so that's what this first part says. We're taking the derivative of a constant times f of x. So let's actually plug in now for the constant times f of x. I'm still going to have the limit as h approaches 0 of. So g of x plus h is now going to be a constant times f of x plus h, because that's how g is defined. Minus, now I have constant times f of x, because that's what g of x is, all over h. And now I can take the limit as h approaches 0 of this thing, and what do I see? I have a constant that I can factor out. So this looks like this now, where I have f of x plus h minus f of x all over h. And now this constant here, you know, from limits, you can pull that constant outside of the limit. So this is really the constant times the limit as h approaches 0 of f of x plus h minus f of x all over h. And this is just the regular definition of the derivative. So in this case, this is just the constant times the derivative of f of x. And that's what we were trying to prove.